Hi, thank you for joining me for the final project for the Duke Machine Learning Foundations for Product Managers course. The project objective was to build a model to predict the electrical energy output of a combined cycle power plant, which uses a combination of gas turbines, steam turbines, and heat recovery steam generators to generate power. The data elements we considered are temperature, ambient pressure, relative humidity, exhaust vacuum, and net hourly electrical energy output. The project highlights were to build a machine learning model based on provided scope and data. The model should predict the potential net hourly energy output of the example power plant based on provided environmental factors. The data provided is in a structured format and continuous, and model effectiveness will be based on mean square error. The model attributes, we used supervised learning, and it's a parametric model. We considered standard linear and multiple linear regression, ridge regression, and lasso regression. I chose standard linear and multiple linear regression just because we didn't want to force the coefficients to low or irrelevant factors or down to zero. And so the model selected, as you can see, is the standard linear regression to determine which variables will be used, multiple linear regression for running data analysis to test the models. And for the project method, we divided the data into three groups, 60% for model training, 20% for model validation, and 20% for model testing. We test each input variable independently with linear regression, and then we'll choose the two highest performing for our model evaluation. Compare two models, which will be based on a combination of the top two performing input variables versus a combination of all four input variables. And we'll utilize the model with the highest performing coefficients of determination for the test data to validate the efficacy. For the data preparation, you can see the breakdown here, the training set for 60%, the validation set at 20%, and 20% also allocated for the test set. And here's an example to the right that you can see of how it was broken down. For the feature selection, it was determined based on results of regression testing, each input variable against the provided PE. The temperature and exhaust vacuum input variables were chosen for further evaluation based on strong performance in coefficients of determination, as seen in the data presented here to your right. And you can look at the multiple R and R square values as to see why we chose these two. For the model performance comparison, the comparison of both models yielded similar outputs with high performance metrics. The decision to proceed with the all input variables models was determined by the below. All input variables had a higher R square value and low standard error versus the AT and V slightly lower R squared and a slightly higher standard error. The model validation, both models were run against the validation data group, and model results for mean square error as shown below. For the AT and V model, you get down to the MSE at 24.5 versus the all input variables model performing a little better with the MSE coming in at 21.3. For the model evaluation, the all input variables model was then run against the test data set. All input variables came up with the MSE of 21.4 if rounded up and an R squared of 0.927 versus the all input variables model with an MSE of 21.8 if rounded up and R squared of 0.924 or 925 if rounded. For the conclusion, the multiple linear regression model incorporating all four provided input variables performed very well when executed on the test data. There was a minimal margin of variance between the validation and test data when comparing the output metrics. This model presented to be an effective approach to analyze current and new data for the power plant to predict future net hourly electrical energy output based on the environmental factors that are tracked and recorded. Thank you.